A pork shoulder is placed in a smoker at 225 degrees Fahrenheit with an initial temperature of 34 degrees Fahrenheit. After 1 hour, the temperature of the pork is 64 degrees Fahrenheit. If your goal is to raise the temperature of the pork to 205 degrees Fahrenheit and you ignore the stall, how long will it be until you can eat dinner? Okay, so a couple of things to know here. So first off, we have problem involving Newton's law of cooling, which is a different kind of growth model, but similar enough that we can take the ideas we've developed so far and work it through. But we will need to begin with the differential model to start with. And so, unlike the last couple of examples, we will need to solve this ourselves using separable differential equations, then get a model to work with, and then start, the rest of the process. The stall, when it says ignoring the stall, so if you've never smoked pork shoulder or anything, which is understandable, around 160 degrees, the temperature stops accelerating quite so quickly. In fact, it actually just stops increasing for sometimes 2 to 3 hours. And so with something like that, our standard growth model wouldn't be able to handle that because the way that the temperature grows would be much different than what actually happens in reality. But we're just going to completely ignore the stall so we don't have to consider it. And let's get started and see what we can do here. So, a couple of things that we do know is some initial points. So we have some initial points, and these are, of course, time and temperature. So, let's use lowercase t and capital T, just because they're named the same thing. But the initial points we have at time equals 0. We have the pork is 34 degrees, so it must have just come out of the refrigerator. And then 1 hour later, we have the pork measured at 64 degrees. Okay, so the other thing that we know is this differential equation, which is the derivative of the temperature with respect to time is proportional to the difference between its current temperature and the temperature of the surrounding medium. So that's what T sub S is. That's going to be the temperature of the surrounding medium. Okay, now, we also happen to know the temperature of the surrounding medium because it's in a smoker at 225 degrees Fahrenheit. So that's just going to be a constant 225 degrees Fahrenheit and not change throughout the problem, which is nice. We don't have to particularly work with it much other than just leaving it as is. But before I plug in 225 here for T sub S, which I could do at this point, but I'm not going to. I'm going to try and solve this differential equation. And to solve that differential equation, we would need to use the separation of variables. So, separation of variables. Now, remember, K is a constant of proportionality. T sub S is a constant of the surrounding medium, the temperature of the surrounding medium. So we don't have to worry about separating those variables since they're constants. It's only capital T and lowercase t. All right, so let's see what we can do here. So the first thing that I could do is try and get everything with capital T to one side. So I could effectively divide everything through by t t minus t sub s. So that would be 1 over t minus t sub s. And then I could multiply d lowercase t to the other side. And so that would leave d capital T here equals k times just d lowercase t is all that's left there. And then we could integrate both sides since the variables are separated. This is going to be a little bit tricky to integrate, but just sort of think, in terms of like if you were integrating 1 over, say, like x minus 4 dx. Okay, so this is a constant, this is a variable. Well, we could have used u substitution, and du would just be dx. So this would effectively become du divided by u, and then integrate with the natural logarithm, and ultimately, well, plus c, of course, and ultimately end up with the natural log of absolute of x minus 4. So that's the way this thing over here will integrate. It's just going to become the natural log of the absolute value of t minus t sub s. Now, if you'll notice, I continually write parentheses around the logarithm and then absolute value, and many instructors tend to just use this kind of notation here. The reason I do this is because in your homework system, it requires all functions to have parentheses surrounding, and then if you're going to have absolute value on the inside of your logarithm, you have to then do another layer of grouping symbols with the absolute value. It's sort of a pain, I know, but it is what it is. So I do this just to get you trained for your homework system. All right, so then that's that integral. The integral over here would just be k times this variable t plus some constant, with which we could now change this into exponentials by basically either raising both sides with a base e, or if we just go directly into an exponential, we have a log base e, so the base of our exponential is e. This would be my exponent, and that would be equal to the argument of the logarithm. So this would be absolute value t minus t sub s. Then at this point, we can actually try and decide if the absolute value even makes sense at all. So the thing is, for this number to be negative, so the temperature of the pork to result in a negative number, is that, or for this expression to be negative, is that the temperature of the pork would actually have to be less than the surrounding medium, which it absolutely is. So this number would actually always be negative. And this gets a little bit weird, but what's going to happen here is we're still going to ignore the absolute value, but we're going to make up the difference in k. All right, so don't worry about the details. I'll explain it later on, but we're not going to worry so much about the absolute value here. All right, now what's next here? So I could add the temperature of the surrounding medium to both sides, and then that would tell me that I have T equals T sub s plus e to the kt plus c, or this is the exact same growth model as we had earlier. And I could rewrite this as c e to the kt, just manipulating that arbitrary constant. So the only difference between this model and the previous is this constant, which is the temperature of the surrounding medium. So it's not much different, so that's kind of nice. Okay, I am going to need this space, so I'm going to erase this material here, if that's okay. And the next thing that I will do is start taking the initial values that I have and plugging into this model. All right, so my model looks like this. So I have the temperature. You know what? I'm going to go ahead and make it a function. Just explicitly state that it's a function of T. Is the temperature of the surrounding medium, which we know is 225, plus some arbitrary constant C, e to the k times T. All right, now, our first point, when I plug this point into this model, what I end up with is the temperature at time 0 is 225 plus CE to the k times 0, which is 34 degrees. Okay. Now I'm effectively just working with this side of the equation here. But watch what happens. All right, so first off, this would be e to the 0th power, which is just 1. So I end up with 225 equals, plus c is equal to 34. And then I subtract 34 from both sides, so let's do that. 225 minus 34 gives me 191. So, or actually I want to bring the 225 that way. So let's say 34 minus 225 would be negative 191. All right, so the initial value here is negative. That's what we're kind of taking up with. Remember those absolute values that I said we could just ignore? That's kind of what's happening here. We're making the initial value negative so that we could ignore it. It works. It works. All right, so my model now looks like temperature at time t is 225 minus 191 e to the k t. All right, that's not all. We have this next point, which we could now plug into this new model and learn what the value k is. So here's what we would do. So the temperature at time 1 hour is going to be 225 minus 191 e to the k times 1, and that output value is 64 degrees. Okay, so let's take this side of the equation then and see what we can learn about the growth constant k. All right, so first thing I will do is take that equation, subtract 225 from both sides. So that would give me negative 191 e to the k equals 64 minus 225. So that's negative 161. All right, and then if I divide both sides by 191, I get e to the k equals, and I'm just going to leave it as this, 161 over 191. Changing that into logarithmic form, what I now learn is that k is equal to the natural log of that, 161 over 191. And I can plug that into the calculator to approximate it. And I'm not sure if it's totally worthwhile, but we'll go ahead and do it. So negative 0.1709. Okay, now, the next thing is to answer the original question, which is, how long will it be until we can eat dinner? All right, so we want the pork to reach 205 degrees before we can do that. So how long will it take to reach 205 degrees? So what we will do is take our newfound model, which is what, 225 minus 191 e to the negative 0.1709 t, and we will set that equal to the value 205. Okay. Just like that. Now we just need to solve for t. So if I subtract 225 from both sides, then that would be what, negative 20 equals negative 191 e to the negative 0.1709 t. Divide both sides by negative 191. So I have 20 over 191, that's a terrible 9, equals e to the negative 0.1709t. And if I change this into logarithmic form, it would be a log base e, so a natural log, of 20 over 191 equals the exponent, negative 0.1709t, and we just need to divide both sides by this value, in order to determine our value of t. So it's the natural log of 20 divided by 191, and then divided by this thing, which I'm going to use the previous answer since it's already stored as many decimals as the calculator can use. And it looks like I get 13.2 hours. All right, and there we go. One piece of advice I can give is just make sure you don't round anything until your final answer, because exponential functions are especially sensitive to changes in how you round, like how many decimal places you use, for instance. And so you can get very different answers even for seemingly small changes to the value of k. So just try and use the entire value of k as you can in order to ensure that you get the correct answer on the homework. All right.